Hi everyone, welcome to another new video from our channel, and this video under the series of Microscopy for Biologists. And in this video we will discuss a very important topic for research in biological science, which is called TEM. So transmission electron microscopy, that's a very important topic to investigate the inner structure of a protein, or let's say in cellular materials, or let's say in nanostructure also. So what happens, electron microscopy use the electrons beam in instead of light, as like light microscopy. Light microscopy use light, and electron microscopy, as the name suggests, use electron to visualize the inner details of a material. Now TEM, the full form is transmission electron microscopy. So here, as you can see here, this is an image of a microscopy. In the upper part of the microscopy there is an electron gun which creates a high energy electrons. Let's say we will see in the next slide 100 kilo electron volt, which has a high energy, and thus it can create a high speed of electrons. Okay, and then it will make an interactions with your matter and make some three type of scattering and make some image. We will see that one in this video. So this video will cover image formations of the transmission electron microscopy. What is the working principle? What is the basic scientific background of the transmission electron microscopy? That we will get in this video. If you want to know the basic principles, working mechanism, what is happening inside the microscopy, this video is for you. Just keep watching. Okay, so high energy electrons, 100 kilo electron volt approx, is going through your sample. Whenever the electron beam is creating in the electron gun in the upper part of the microscopy, that electron has high energy and thus has a high speed. Okay, now this is so much high speed that some electron beam actually go throughout the sample, like the middle one, without making any disturbance in your sample, without making any interference with your sample. This is called unscattered electron. The one type of interactions is called unscattered electron that goes throughout the sample without making any disturbance to your sample. Another type of interactions happens when it goes and make interaction with the nucleus. It bends off, it bounces off your pathway by the nucleus, and when it hits the nucleus, and this we call elastically scattered electron. What happens? As the definition suggests, elastically scattered means two molecules or two body comes and make an elastic scatter, the elastical collisions, in which your speed, your energy will not change, but the only thing will change the directions of the movement of the high speed body. Okay, so that actually happens in this case also. You have the electron, this is coming and making interactions with the nucleus. This is called elastically scattering. So here, by elastic scattering, no change in speed, no change in energy of the electron, but the only thing change is the directions of the electron beam. This is the type 2 interactions. These two type interactions, this elastically scattered and unscattered electron, this actually contributes to image formations of your transmission electron microscope image. But you can't avoid a third type of interaction that is bad for us. We don't want, but that happens naturally. That is the interactions of an electron with another electron, which is revolving in the sample, which is revolving in an atomic orbital of your sample. Okay, so here this called inelastically scattered electron, which actually transfer some energy to your sample. Okay, and this actually causes a serious damage to your sample, and that's a real drawback of the transmission electron microscopy. So one thing again to remember, the unscattered and elastically scattered electron contributes to the image formations, but the noise actually formed by the inelastic scattered light, this is the bad scattering. We don't want that. This contributes to the noise formations of the image. So whenever you will get image, you have to first cancellation the noise, and then you can only go to the 2D image. From there you will get the 3D image by some software that we will see. Now the point is that how the image looks like, how the transmission electron image looks like. Okay, so this is a peculiar type of transmission electron image. Here are some virus are there. Here are some virus picture which has been captured by the transmission electron microscope. Now you can see this is actually a white and black picture, and this type of old days picture, not like today is a colored cinema. Okay, so as we know, old are gold. That's why you will see transmission electron microscopy can go to the resolutions of 0.019 nanometer resolution, so it can go to the subatomic resolutions. But light microscope can go to that one. It can go up to 200 nanometer. Okay, so that's why light doesn't interact here. That's why here electron is interacting, and that make a contrast of your image. Contrast means you have white and someplace you will have black. That type of image you will get from your electron microscopy. No colored image. That's why we will say contrast. And if you understand what is the basis of forming a contrast in your image, you can be helpful to understand how the image formed. So the basic principle of image formations of the transmission electron microscopy is just the contrast formations. In the next slide, you will see how the contrast forms. So there are two types of contrast: amplitude contrast and the phase contrast. We will see in the next slide. There are two types of contrast. One is amplitude contrast, another is the phase contrast. So this slide concerns about the contrast formations. Amplitude contrast is useful for visualizations of the compartments of cell. Different compartments of cell can be visualized by the amplitude contrast. And this type of image you will get. And this is exactly same as like the X-ray. As you can see here, this is the X-ray. So amplitude X-ray image, amplitude contrast forms as the same principle as that of the X-ray. Whenever you will go to the doctor, they shows you the black and white image of your bone, of your bone marrow, of your any other structures. So what happens there? What is the mechanism? The X-ray or some subatomic particles is going to penetrate your body and making the image. By how? Which mechanism? That whenever you have bone is actually dense as compared to the soft tissue. So whenever you have bone, there are more scattering of that subatomic particle and create a black, and the soft tissue less scattering creates white spot. And you actually can see in your doctor's image, in the X-ray image, the opposite of that. That's why you can see the bone, that is the white, and the soft tissue, that is the black. But the principle is exactly same. Whenever you have exactly same for the TEM also. So TEM use the principle. Transmission electron microscopy uses the principle of amplitude contrast formation as like of X-ray, which is helpful to visualization of the compartment of cell. Which is the basic of that contrast formation? Whenever you have more density, then lots of scattering, more density of electron, then lots of scattering. And one thing, this scattering is actually elastic scattering, not inelastic scattering, because inelastic scattering contributes to the noise, not in the image formations. Image formations only done by elastic scattering and unscattered electron. So lots of scattering appear dark. Lots of scattering of with your materials. When you material you have the dense part, then lots of scattering will happen, and that will be appeared as a dark in your image. And you have less scattering, then the brighter spot will come in your image. But whenever you want to do some macromolecular structure or the protein internal details of a protein structure, then you can't rely on the amplitude contrast. You have to go to the phase contrast. Phase contrast is just for macromolecular complex details and protein details. People use the phase contrast method. And here what happens, you have the elastically scattered electron, you have the unscattered electron. These two electrons are interfere to generate a greater contrast, and phase shift happens for this contrast. Phase shift happens, and this is the reason of the contrast formation is the phase contrast, which is helpful to the macromolecular complex details. Now we will again come back to the Amplitude contrast. What happens? What is the mechanism of amplitude contrast formations? Now they use a open aperture. This is the objective aperture has been shown here, which is used to eliminate the dotted lines. Dotted lines here denotes the elastically scattered electrons, but the solid line denotes the unscattered electrons. So whenever you will put an open aperture just after the objective lens, then the specimen here, incident electron beam is going through the specimen, and the elastically scattered electron are going to be removed, cannot go throughout the aperture, but the unscattered electron can go throughout the aperture and make the image. Now the principle relies on the fact that traditional image forms by the basis of incident electron being scattered and disappeared based on the compositional density of the materials as well as the crystal orientation of the sample. That means, in a very lucid language, that if you have the high electron density, if you have the compositional density very high, then you will get more scattering, and you will get a dark spot. Whenever you have very less electrons, you will get a bright spot. That's the basic principle of the contrast formation. And contrast formation means the image formations in the electron microscopy. Now here is the typical instrument where you can see the high voltage. High voltage is applied here, which helps this electron gun to create electrons with very high speed, high energy. And then here the electron beam, high speed electron goes through the vacuum inside the microscopy. This sky color is actually denotes the vacuum inside the microscopy. And this you can't use here the normal glass lens. That's why people use here electromagnetic lens, has been denoted by first condenser lens and the second condenser lens. So that used to make a fine electron beam of the high speed running electrons. So here fine electron beam has been formed, and then you have the sample. Here you have the sample. So sample, here you have the sample. Then high speed fine beam of electron goes through the sample, penetrate through the sample, and here you have the objective lens and aperture. You know the why aperture is used, because to remove the elastically scattered electron. Then the electron beam comes from the specimen, goes to the bottom screen, which is called a fluorescence screen, and make image. And this has been projected to another screen which is directly connected to the computer and gives us the image. We will see in the next slide how the image formations happens in a more details. So this objective lens and aperture actually used to remove the elastically scattered electrons, and here the electron beam coming through the specimen has been captured in a screen at the bottom of the microscope, and that has been projected to another screen. Like here you can see, this is the electron beam coming through the electron gun, and here is the sample. This is the high energy electron beam, and then it will be reflected to a screen here at the bottom of the microscope, and that will be projected to here, and that will be projected to here, and that makes directly connected to the computer, which makes the image like this. This is a sample of TEM image where there are some nanoparticle has been imaged by some transmission electron microscope. Here is the dark spot, shows you have more electron density, and the bright spot, no darkness. Bright spot shows there are less electron density. Okay, from there, okay, one thing to mention, this image you get, this is with noise. So how you will get the exact 3D image of the protein? What the people do, what normally we do, we make the specimen on the specimen sample chamber of the electron microscopy, and then we take, by moving in this projection screen, by moving on this, the below projection screen, the bottom of the microscope, we take the images of, let's say, 15 to 20 areas of that specimen. 15 to 20 areas of the specimen. Now, when we will analyze the images, we do first 15 to 10 images in a software, and then average it. When you are averaging, the noise is being cancelled out. So after averaging out, you will get without noise image, but it is 2D. It is in 2D image. but you have to get the 3D image. Then by some another image processing, we will discuss some another video, they will get the 3D image of the protein. So first noise cancellation and then the 3D image formations. Okay, and now we will see what happens, what actually are happening in the exact transmission electron microscopy. Let's take the video. First, just a minute. So here what happens, this has been taken from quantum made sample. Here the bottom screen, here the lenses, here the electron gun. Now electron will come. This is the sample chamber. This is the sample chamber. This is the lenses. Now electron beams are coming. Now making an interactions with the sample, penetrate through the sample, going through the lens, making a very image forming beam and make an image here which has been projected in this screen. Make an image here in the bottom of the microscope and which is projected to this screen. This screen actually connected with the computer. Now the last things we want to discuss, what is the difference of the light microscopy and the transmission electron microscopy. Light microscopy uses the light. Light microscopy uses the light which penetrates throughout the sample, and TEM uses the electron. Now normally for this use of light, the resolution is the sharpness of image what you get. How much inter details you can investigate from that image, that's called resolutions. So the resolutions is limited by the wavelength of the light, which can magnify a point up to 2000 times for a light microscopy. But as I have said, old are gold. That's why the non-colored, uncolored, as like old picture are the gold. This can go to the 0.1 nanometer resolutions. This use, okay, TEM can produce much more magnified image up to 2 million magnifications, can go to the subatomic level. Resolution power is approx 0.1 nanometer because here you are using electron. So the same, so electron has very smaller wavelength which creates the image of very high resolutions. Hope you understood all the concept. So once more I want to give a short descriptions what is happening in the transmission electron microscopy by this video. Okay, first this is the bottom screen. Okay, and this is the lenses. Here you have the lenses. And here is the bottom screen. Now here is the electron gun and this is the sample. Now electron beam is coming throughout the lenses. A fine electron beam has been created and then interacting with the sample, and then again the interfered or scattered or electroscalar electron beam has been captured as an image in the bottom plane as a screen, and that has been projected to another screen, and this has been created a fine image in your computer. This is the basic. Okay, this is the basics of transmission electron microscope. Hope you understand all the concept. If you have any questions about that, just ping me in the comment box, and you can mail me also in that mail given in the descriptions of this video. Thank you guys for watching, and please share and subscribe if you like it helpful.